So hello everyone, I'm Bhaskar Kataria. I'm a second year PhD student at Cornell. Today I'll be talking about our work learning to tune optical WANs, field deployment of noise model in optical networks. So optical WANs are the physical backbone of internet and cloud infrastructure. These are massive and expensive. They are a billion-dollar infrastructure. They comprise of hundreds of thousands of miles of fiber with thousands of optical devices. And all these optical devices, they interact differently and they shape the optical power throughout the network. So let's look at what are the main components of this network. So here we have node A and node B, which are connected through the main components of the network. Let's take a look at how all these components look like. So first we have transceiver, so which converts the signal from electrical domain to the optical domain, and on the receiver side, it converts it back from optical domain to the electrical domain. Then we have ROADM, which are like routers. They route wavelengths between different fiber spans. And then we have fiber span, which carries the optical fiber, which carries the optical signal. But during the propagation, because of signal attenuation, it loses some power. And that's where amplifiers come in. So amplifiers, amplifies the signal for the fiber to compensate for the loss. So here, let's look at what does the optical power profile looks like. So in this network, the transmitter is transmitting the signal and the receiver is receiving the signal. So here, you can see as the signal propagates over the fiber, the optical power keeps on reducing. And because the optical power gets too low, the receiver is not able to decode the signal properly. But here, if we add an amplifier, which could amplify the signal, then the optical power would again increase, and you would receive the signal. And to control how much do you want to amplify the signal, there is a configuration in the amplifier called gain target, which controls how much do you want to amplify the signal. With higher gain target, you get higher optical power. With the lower gain target, you get lower optical power. So it is pretty simple. So what you want is you want higher gain, but the problem is when the signal propagates over the network, you also get noise, and the noise keeps accumulating over the course of the signal propagation. So what we want ideally is a higher signal, more signal power and lower noise, or in other words, what we want is a higher signal to noise ratio. With higher signal to noise ratio, we can encode more bits, and if we can encode more bits, then we get higher bandwidth. So yeah, what we want is a higher SNR. So we can keep on increasing the gain. That would increase the optical power, and so what we want to keep is if we want to keep the highest SNR, it's simple if we increase the gain, but more gain is not always better. So here, as you can see, on the y-axis we have end-to-end SNR, and on the x-axis we have gain target. The end-to-end SNR increases till here. You can keep increasing the gain target, and it increases up to a point. But after a point, the noise starts dominating, and that's when your end-to-end SNR starts to suffer. So tuning an amplifier is a peak finding optimization problem. What we want to do is we want to find the peak and optimize for it. We don't want it to be too low, otherwise you would be wasting capacity, and we also don't want it to be too high. Otherwise, we would have higher noise. And in some severe cases, it could damage the downstream components as well, and which could end up killing the network, and that's what we don't want. So here, we saw that tuning an amplifier is a peak finding problem. So okay, we can find the peak, but there's not just one amplifier on the network. You have multiple different amplifiers on the network, and it depends on the length of the network. So the longest optical fiber system is about 45,000 kilometers, and you need an amplifier at every about 50 to 100 kilometers. So that translates to at least 450 amplifiers in this optical system. And to make matters worse, different amplifiers have different gain profiles, and they reach end-to-end SNR at different values. Moreover, there are different types of different vendors, and all of them have their own proprietary configurations, and there are different types of amplifiers. You have ADFAs, which has their own characteristics. They have less noise, more noise, higher gain. Raman amplifiers, which has higher gain, less noise. So how do operators do it right now? So So what operators currently do is they use the vendor-specific control plane to adjust the configuration by a small margin, and then they measure and validate if the end-to-end network is performing well, and then they keep repeating this process. So this process is slow. You need to adjust and validate. Moreover, the process is risky because the network could go down. So because of this, the operators do it very conservatively, and it leaves the optimization opportunity on the table. So we asked the question, can we find a better configuration without touching the live WAN? And that's what we do in this project. We model the optical network, we find the optimal configuration, and eventually we deploy. So in this talk, I'll first describe the network that we modeled. Then I'll talk about how did we model the network, followed by how did we optimize the network, and finally, I'll talk about how did we deploy and what were our results. So for this, so here we used NYSERNet, a production New York State optical WAN. It's a nonprofit research and educational ISP. We modeled two segments of this network, one from Albany to New York and from Albany to Syracuse. We modeled all the main components of the network. So let's look at the single direction physical view of NYC to Albany segment. So here first you need to route the signal. So first you have a ROADM. Followed by now, when you have routed the signal onto the fiber, you need to amplify. So you have a high gain EDF amplifier. As the name suggests, it has a higher gain profile, and it increases the gain by a bigger value. Then the signal propagates onto the fiber, and as the signal propagates, you get some fiber attenuation. So here in this case, it's about 17.7 decibels. And then to compensate for this, we have another amplifier. So here, this is a different sort of amplifier called Raman amplifier. And here, we are using two different sorts of amplifiers in the network. With EDFA, you get higher noise. With Raman amplifiers, you get lesser noise. EDFAs are primarily used to hit the desired output power, so the output power doesn't get too high or doesn't get too low. Raman amplifiers, because of their lower noise profile, they are primarily used to increase the span. EDFAs are much easier to operate for the operators, and Raman amplifiers, they are much more difficult to operate. So why are both used? EDFAs, they give an overall simpler control than Raman-only system, and Raman, they give overall better SNR than EDFA-only system. And the next few components, you have a lower gain amplifier, which has a lower gain profile if you want to amplify the signal even more. And when the signal amplification is not enough, you generally pair multiple amplifiers together, and then the similar setup going ahead. So in a case where if you have the amplification is too high, the optical power is too high, and it could damage the downstream component. So typically what people use is an equipment called jumper, which attenuates the signal and reduces the optical strength. Yeah, followed by, this is how we, so this is, that was the physical view of the network. Let's look at how do we model the network. So for modeling the network, we used a Gaussian noise abstraction. So here with Gaussian noise, what we want is that what we know is each component adds its own noise. Each component adds its own noise, and here we assume a few things. First, that the noise is additive. So here, as in the graph, we can see we have an original signal, and if you add a Gaussian noise, what you get is a noisy signal. Moreover, we consider that the different channels on the network, they are independent. So what that means is here you have power versus frequency for different channels on the fiber. If you add Gaussian noise onto the fiber, the noise gets added to the signal independently to each channel, and it accumulates over the path. So if you have noise source 1, it would be accumulated added to the frequency, and then similarly for noise source 2, it will again get added. We implemented this with a framework called GNPAP. So in this, I'll focus on amplifiers. How did we model the amplifiers for the time constraint? So for modeling EDFAs, I'll first explain how EDFAs work. So EDFAs use a short erbium doped fiber as the gain medium, and then it uses a pump laser to excite the erbium ions. And when the signal reaches the amplifier, the photons trigger stimulated emission, and the signal gets amplified. With this, you get an immediate increase in SNR. But because of spontaneous emission, noise also gets added, and which results in a lower SNR because of the noise. On the other hand, Raman amplifiers, they use the fiber itself as the gain medium. In the fiber, they use a pump laser in the direction opposite to the signal. So if the signal is going towards from transmitter to receiver, the pump laser is sent from receiver to the transmitter. And the strength of the laser is closer towards the amplifier and weaker towards the transmitter. So the gain is distributed along the fiber. It is higher towards the amplifier and lower towards the transmitter, but the gain is overall distributed towards the fiber. What you get is a higher SNR than EDFA, because the signal doesn't get too weak, so the noise doesn't, it gets improved before getting too low. However, gain depends on two things. First, the fiber, because now you're using fiber as the gain, fiber as the medium, so it depends on the fiber. It also depends on the pump. So since you have multiple different channels in the amplifier, you have different pumps for each channel. And all of the channel-specific information for pumps, they are proprietary and not available to us. So what we did for Raman amplifiers was we modeled them as EDFAs with low noise. So here what would happen is with EDFAs, you would get a higher gain and a lower noise profile. And this is how we modeled Raman amplifiers. And few other hurdles in the modeling were like heterogeneous equipments. There are lots of different equipments, and with all of them having their own varied parameters. Most of the equipments had their proprietary device behavior, missing vendor-specific information, so for which we had to either approximate or use publicly available information, and modeling Raman amplifiers because of proprietary pump characteristics. But with all this, we were still able to model with a good accuracy. So here, as you can see, for different channels across, we get error, the maximum error of 3.5%, and overall error is less than 4%. So we can faithfully model the network with a good accuracy. Now that we have modeled the network, we wanted to see if we can use this model to actually optimize the physical span to tune the configuration. So let's look at how did we tune it, like what are our optimization constraints. So for this, here we tune the gain profile for all the different amplifiers. We tune them in the steps of 0.5 decibels. We'll limit them to safe values so that the amplifier, the equipments don't get damaged. And another important constraint was for Raman amplifiers, we keep the gain at the maximum value, because since they have lower noise, you get a better SNR with them. And even with NYSERNet, in the deployment, they always keep the gain at the maximum value. So with this, we searched through all the different configurations. And with this, we were able to find the highest SNR available. So here we have SNR on the y-axis and the trial iteration on the x-axis. Each blue dot represents one iteration, one configuration. So with all the different configurations, we were able to, among all the different configurations, we were able to find the optimal configuration. So now we have an optimal configuration. And what do we do with the configuration? We would want to deploy it. So for deploy, we used a phased and a cautious approach, wherein the maintenance we used, under the operator supervision, we created a maintenance window. We changed the gain in small phases with 0.5 decibels. And after each change, we would monitor after each step. And we planned to roll back if anything went wrong. And we measured, after each change, we would measure to confirm stability. And what we found was, here on the left-hand side, we have the transmission node from NYC, where the optical signal quality doesn't change, because this is where the optical signal is transmitted, and there is no change there. But on the right side, we have two graphs from Syracuse and Albany. And as you can see, there is a SNR bump for both of them, and it stays stable for the continuous duration. With this, we were able to achieve 4.2 decibels of increased SNR across all three wavelengths. And this resulted in a 10.4% capacity increase, and which translates to about 60 Gbps increase in the capacity. So to conclude, we modeled a live production optical WAN with all the main components. We achieved less than 4% in modeling. So we could faithfully model the network. We optimized the configuration by tuning all the different gain parameters. And then finally, we deployed the optimized configuration, resulting in capacity increase by 60 Gbps. That's all from my side. Thank you.